thanks, Jake, and thanks to the organisers for inviting me. Is there an echo for you guys or just for me? Okay. Yeah, so I'm going to talk about something completely different. I don't think I've actually talked about the blob complex to a link homology audience before, so I'm going to actually talk about it in a slightly different way and actually give you the honest historical perspective on the blob complex, because the whole idea for it actually came about while thinking about some things to do with cohomology. Usually I omit that entirely when talking about the blob complex, but I'll try and explain that today. This is joint work with Kevin Walker. There are copies of these slides online, and there's indeed a copy of the paper corresponding to this talk at my webpage, but not yet on the archive. So, I just wanted to put up this great quote from Yuri Menin. Homological topology and TQFT have grown so close that, well, so on. And I really liked this quote when I saw it, because the point of the blob complex is really about sort of taking homotopy theory and TQFT and smushing them together and seeing what you get. So I'm going to just give you a bit of overview first about what sort of gadget the blob complex is and what you might do with it. Then I'll remind you a bit about TQFTs, or maybe just tell you the way that we think about TQFTs. Then I'll give the definition of the blob complex, and then I'll tell you some things we can prove with it and about it. So, what is the blob complex, first of all? It's a gadget that takes an N manifold and an N category with some sort of duals, we'll get to that, as input, and it produces a chain complex. So we're going to write this B star of M, the manifold, with sort of coefficients in some category C. Now, is it possible to move this? I have to keep on coming back to the keyboard here. Okay. Now, before actually telling you the definition of this gadget, I just want to show you how it's related to a few things that you might already know about. In particular, it has a bunch of special cases that recover some interesting things, but very different interesting things. And I think that's part of the promise of the blob complex. It puts a few interesting things together. So one thing that you can do is you can take this chain complex you get and compute its homology and just get a graded vector space. And then just look at the zeroth graded vector space, the bottom one. And that recovers for you, well, what I've written here is A of M semicolon C, which is the usual TQFT vector space associated to an M manifold and an M category. I'll come back again in a moment and tell you a little bit more what I mean by that vector space. So the zeroth homology of this blob complex is recovering TQFT vector spaces. But we can specialize in a different direction. Let's now just set n equals 1. So we're looking at a 1 manifold, a circle, and a 1 category, which might as well just be an associative algebra. And in this case, the homology of the blob complex is exactly the Hochschild homology of that associative algebra. And so once you've seen these two specializations, you should be thinking that the higher homology for the blob complex for some n manifold is something like what Hochschild homology tells you about an associative algebra, but for higher dimensional manifolds. And then the final one just sort of shows that you can recover some of the topology of M by this construction. So if you just take any commutative algebra, for example here, just polynomials in a variable, there's a way of thinking about any commutative algebra as an n category for any n you like. And so you can plug that into the construction, and here you get the singular homology of the infinite configuration space of the manifold star. And there are a few variations on this that let you recover other bits of topological information about the space. I'm not going to talk at all about that arrow down there for the rest of the talk. Okay, now it's going to take a little while before I actually define what the blob complex is, so just keep in mind that information about what it specializes to. To get there, I'm going to first of all say a little bit about n categories and a little bit about TQFTs and then a little bit about the motivation for this whole thing. Now, n categories are unfortunately a pretty scary subject. They're at last count 19 or so different definitions of n categories, and to see that any two of those definitions have anything to do with each other, you have to take the n categories on one side and think of them as an n plus 1 category, and the n categories on the other side and think of them as an n plus 1 category, and then try and see these n plus 1 categories are the same, but you're still using different definitions. It's horrible. So to add to the mess, we just have yet another definition of n categories that are sort of optimized for everything that we want to do, and I would say optimized for thinking about TQFTs as well, but you can argue about that. Fortunately, for most of the definition, I'm just going to draw two-dimensional pictures and pretend them as a surface, and so you can pretend that an n category is just a tensor category or a pivotal category, something like that, and you'll understand most of the pictures. Oh, I'm not actually going to tell you the full definition of our notion of a topological n category, but I just want to tell you the essential ingredients so you can see them as they get used. So first of all, one of these n categories, so it's written as script C, or curly C, all through the talk. It associates a vector space to every single ball, that is, every manifold that just happens to be homeomorphic to the standard ball. And then the important thing is that it also gives you some maps that you glue together balls. So say I have some big ball, and it's chopped up, say I have a cell complex, and on each of the top dimensional cells that make up this big ball, I've given you an element of the vector space associated with that smaller ball. Then there's a map that lets me assemble all these together and get a vector associated with the big ball. So this is just, in any definition of an n category, you have to have ways of composing morphisms, and this is all of that packaged all together at once. Just for an arbitrary decomposition of a ball as a cell complex of smaller balls, we can glue together those vectors associated with the smaller balls. Now, I wrote this map as a tensor product over all of the smaller balls of those vector spaces to the vector space associated with the big ball, but I don't really want the tensor product here. An axiom that I haven't written here explicitly is that whenever I have an element of this vector space associated with the ball, I can say what its boundary is. So there's some set of possible boundary values for each ball. And I only really want to take this tensor product where all of the boundaries agree. So if I have a big ball, it's divided just into two parts, two balls glued together, and I give you a vector in one ball and a vector in the other ball, their boundary data has to agree on their common boundary before we're allowed to glue them together. Okay, so there's this big list of axioms, a few more that I'm not showing. And I just want to say that sort of the axioms, there's sort of a maximal set of axioms for an n category. And so we're not claiming that it should be easy to check that any particular example satisfies our axioms, although some it's easy to check.
Sorry, I have a question.
Yeah.
What do you mean by for every n ball? I mean, is it the same vector space?
Okay, so really what I want is let's just look at the category of n balls. So the objects here are manifolds which happen to be homeomorphic to the standard ball, and the morphisms are homeomorphisms between balls. So I want to associate a different vector space to every single different n ball, but for each homeomorphism, an isomorphism between those vector spaces. So you've got to provide me a lot of data to specify one of these n categories. And it's really essential that we give different vector spaces for different balls so that these gluing maps can be associative. Usually it's a big problem if I have, this is just like seeing that pi 1 of a space is associative. You have to do all these reparameterizations. We're sort of avoiding those issues. We can just ask for things to be associative on the nose because we're looking at maps of different things that happen to be intervals rather than one standard interval we have to identify every other interval with.
Why is the vector space the ball and the boundary? Did you say that?
Okay. So we're just going to associate a set to each of the n-1 spheres. And really what I mean is that for each element of that set of boundary conditions for a ball, so for each element of that set, there's a vector space. So really it's like a whole collection of vector spaces, one for each set of boundary conditions.
The question was rather typical when you are talking about n-dimensional TQFT to n-manifold, you associate a number, not a vector space.
Oh, okay. So in this perspective, from one of these n categories, we're going to produce what some people call an n plus 1/2 dimensional TQFT. That is, it associates vector spaces to n manifolds, but it doesn't necessarily associate anything at all to n plus 1 manifolds. Yeah. You need extra structure beyond what I'm going to use here at all to give you that top level. So this is like in Taranto invariance, the input there is a 2 category, and you get vector spaces for 2 manifolds, and there happens to be a way of producing numbers for 3 manifolds, but we're not touching that, and we're not using any of that stuff. Okay. So what do you do with one of these topological n categories? Well, I want you to think about the category of cellulations of a manifold. So here the objects are ways of writing the manifold as a cell complex, and the morphisms are anti-refinements, taking some adjacent cells and gluing them together to form another cell. So this is this picture here is just a very small part of the cellulations of a 2-disk. Okay, but now anytime we have an n category, we get a functor from this category of cellulations of M, 2 vector spaces, on a level of objects. So it takes, say, this particular object here, and, well, we know how the category tells us a way to associate a vector space to each one of these cells, so we can take the tensor product of all of those, again with this condition that the boundaries have to agree. And now that associates a vector space to each object here, and what do we do with the morphisms? Well, given an anti-refinement here, this one is gluing all of these guys together to form a single ball there, and those two to form a single ball there. The structure of the category gives us a gluing map for each piece of that anti-refinement. So the linear map we associate is just that anti-refinement. Okay? Now, with that notion, I can tell you what I want to call a field on M all the way through this talk. So a field on a manifold is a choice of cellulation, so we write it as a cell complex, and then we pick an element of this vector space for each one of the cells, for each one of the top cells. And again, with the condition that the boundaries match. Okay, so here's an example, and hopefully it'll start to make sense again. So I want to show you here an element of fields on the 2 torus when my example category is the temporally leaf category. Okay, so I've taken this torus here, and I've chopped it up into pieces that are homomorphic to balls, and then inside each ball, I've written a morphism from the temporally leaf category, and I've made sure that all the boundaries match up. Okay, so that's some gigantic vector, truly gigantic vector space. I mean, every single different cell complex for the manifold gives you a different direct sum and of this vector space. Okay, so I also need this notion of a null field. So if I have a field on a ball rather than just on some arbitrary manifold, I can just apply the whole gluing map at once. You just glue all of the cells together to get a single big cell that occupies the ball. Okay, so that's some map from the set of all fields on the ball to just the vector space associated with the ball. And I'm just going to call a null field anything that evaluates to 0 under that map. So here's an example. These 2 terms here are genuinely different fields, okay, because, well, they both have the same underlying cell complex, but, well, the fields are just different. However, when you evaluate these in the temporally leaf category, that just means forgetting the red line, these become exactly the same morphism in the temporally leaf category. Maybe I should have used an even simpler example. I mean, the only relation in the temporally leaf category, if you don't know this, is that a closed circle is equal to some parameter d. So these 2 pictures are exactly the same once you erase the red line. And so this difference is an example of a null field. Okay? It sort of captures all of the local relations in the category. It's like giving an algebra by generators and relations. The fields correspond to words in the generators, but they're words written on a manifold rather than a line, and the things that are null fields are exactly the relations. Is this horrible? Nice? How confused are people? Okay, let's see what happens on the next slide. Okay. Yeah.
With temporally leaf, right, there's sort of a top and a bottom. And I mean, when you just chop up into cells, I don't know where that is.
Yeah, so in our notion notion of an n-category, morphisms don't have preferred tops and bottoms. So if you give me a ball and you tell me a decomposition of the spherical boundary into a northern hemisphere and a southern hemisphere, then we're allowed to talk about the source and target. That's just the boundary data for this guy restricted to the top and bottom. But ahead of time, who cares? We don't force you to make choices of northern and southern hemispheres of balls. So this isn't quite the temporally leaf category you're used to. It's this temporally leaf category, just reach disk, you throw some spaghetti in the disk, it meets the boundary, and some circles inside.
But then do you have a notion of what it means to be a morphism? I mean, there's no direction of morphism.
No, there's no direction of morphism. So the thing to think about here is that this notion of an n category has duals built in really fundamentally. So a good way to think about this is, say you have, just say in a tensor category, you're looking at home from x tensor y to z. Well, in the presence of duals, if your tensor category has nice duals, then this home space is canonically isomorphic to home from x to z tensor x dual. Okay? Oh, sorry, thanks. Quite. And this is sort of just saying that, well, say we have this disk with some boundary points marked x and y and z. We could think of this as the incoming piece of the boundary, and that is the outgoing, or we could think of this as the incoming, and that is the outgoing. And so what we're doing is, rather than having a different vector space for each way of dividing up the boundary into source and target, and then identifying them all by having duals, we're just having one to begin with. Yeah, it's not your usual definition of n category, and it takes a little bit of thinking to recover the usual notions for n equals 1 and n equals 2 and so on. Okay, so once you've got this set up, we can associate a single vector space to a manifold or a much smaller vector space. So we start by taking all fields on the manifold. Okay, this is some gigantic vector space. But then we quotient out. We kill any field on the manifold for which you can find some ball inside of that ball, so that inside of that ball you have a null field. That is, if there's some ball where if you apply the evaluation map inside that ball, you get to 0. Okay? We kill off those things. Now, this vector space is the usual TQFT vector space that you might know and love, but said kind of differently. In particular, if you give me a fusion category, I'll think of that as I'll insist on thinking of that as a 2 category, and now we do this construction for a surface, n equals 2. This is exactly the derived 0 vector space that you get out of that. Now, another way of thinking about this definition, all fields modulo fields which evaluate to 0 inside some ball, is saying that this vector space is the colimit along along the cellulations of M of this function we defined from C. So this is just saying that for each cellulation, we assign some different vector space. And if you just take all fields, you just take the direct sum of these vector spaces. But now, anytime there's an arrow, we're just identifying any vector in here with its image in here. That's the definition of the colimit, and it's easy to see that that's the same as the first thing I said. Okay. So that's a scary definition because it takes some gigantic vector space and takes some quotient. But you can actually you can prove a gluing formula for this definition of the skein module for an n manifold and an n category, and that's what's on the bottom of the slide. So if you take an n minus 1 manifold y and cross it with an interval, we have an n manifold now. I claim that you can give the vector space that you associate with an n manifold the structure of a 1 category. If I have y cross I and another copy of y cross I, what? But I have a field on y cross I and another field on y cross I. I can glue those fields together to produce a field on y cross I union I, and then identify the I union I with standard interval. And that gives me a product on this vector space. You're upset about the equivalently, I said there, the two different definitions of A and N. Okay.
It seems like there's a lot more stuff that you're finding out by in addition to what you just said, which is, and what you just said is what you need to find out how to over.
Okay, so you're saying that in the co-limit I'm modding out by too much stuff. Okay. Well, so really what I'm doing here, when I say that I identify any vector here with its image up here, that's just the same as saying that any vector here, which gets sent to 0 up here, I set to 0. Okay? Now, a vector here that gets sent to 0, well, that's saying that that inside the ball, so I mean, let me just draw a picture where I'm only gluing two balls together at once. So all the left-hand side is staying the same, I'm just gluing these two balls here. Okay? So if I have a vector here that's being sent to 0 here, that just means that the piece on the left here must be 0, and so that means that the field I had drawn on those two balls was exactly a null field. Okay, so what does this gluing formula let you do? Suppose you have, so y cross I for any n manifold y forms a category. If I have y as a submanifold of the boundary of x, then the vector space A of x becomes a module over A of y cross I. And now the gluing formula says that if I have some x, and I have two copies of y in the boundary of x, well, that means that A of x now is a bimodule over A of y cross I. And the theorem just says that if I take x and glue up those two copies of y in the boundary, the skein moduli associated to that is the sort of the self-tensor product of this bimodule to identify the left and right actions of this category. And although it doesn't look very much like it, by thinking about handle decompositions or cell decompositions and so on, you can translate this gluing formula into the state sum formulas that you're used to seeing for calculating TQFTs. Like the state sum formula for derived derivative theory is a pretty easy consequence of this gluing formula. Okay, so that was a lot of sort of scary background about how we think about topological quantum field theories. And now let me just show you how this lets you do something nice and very easily with Cohomology homology. So, I mean, wanting to do this was sort of the origins of the blob complex. So, first of all, you can notice that Cohomology homology gives you a 4 category. There's a 4 category underlying Cohomology homology. And so, on this slide, I've just said what the 3 morphisms and 4 morphisms are. But I know from talking to people at lunch yesterday that that's a bit terrifying, and I should tell you what the 0 and 1 and 2 morphisms are first. So let me add those here. So in this 4 category, there's only one 0 morphism. I'm just going to call it a point. And there's only one 1 morphism. I'm just going to call interval. It should be obvious how to compose 2 intervals to get an interval. Okay, now the 2 morphisms are squares with some number of points at particular locations in the square. So the source and target of this morphism here are both the interval. Okay? And now we can get back to the slide. Well, a 3 morphism better be a map from one of these pictures to another one of these pictures, and I just want to take a particular tangle embedded in the cube that starts at some set of points and ends at some other set of points. Okay? So far we've described the 3 category of tangles. You can compose if I have if I have a tangle and another tangle, I can stack them on top of each other. That's the composition of 3 morphisms, but I can also stack them side by side in 2 different directions. And those are the 3 different operations that we have on 3 morphisms. Okay, so to get a 4 category out of Cohomology homology, what do we do for the 4 morphisms? Well, if I have 2 of these tangles embedded in in a cube, and they have exactly the same boundaries, so the same points in the top and bottom, then I can take these two tangles, take the mirror image of one and glue them together. Okay, that just gives me a knot in S3. And the Categorification homology of that knot is some vector space. So I declare the set of morphisms from one tangle to another to be the Categorification homology of the knot you get, the link you get by gluing the two tangles together. Now, I need to tell you how to compose four morphisms, and maybe I'll just say that you define that using some cobordisms, and say we're really using strongly here the functoriality of Categorification homology in order to just even define composition. So you should think if I have, just to sketch that, you should think if I have the Categorification homology of T1 union T2 mirror image, tensor product of the Categorification homology of T2 union T3 mirror image, how do I produce a map from the Categorification homology of T1 to T3 mirror image? And it should be pretty clear that there's a very sensible cobordism to use that gives you a map from here to here. And that's how we're defining these operations. Okay, so, hooray! We've got this fantastic four category. So what do we do with it? Well, we just run the picture that I described before, and we have a four manifold invariant. Great. So, what exactly is it? Well, given a four manifold, possibly with boundary, but if it has boundary, we have to specify boundary conditions, and that consists of a knot in the boundary, we get this doubly graded vector space. So I've written there A of W, L with coefficients in the Categorification homology four category. Yeah.
I'm still very confused about this. So you've got this four category, but most of these morphisms are just these topological objects.
Absolutely.
The four morphisms, all this that we're talking about some sort of extra construction.
Yep.
Homology and just okay.
Well, okay, so let me maybe do an example one level down that might help. So here, let's see. So let's say, I'll say two different things to try and clear this up. So first of all, here's Categorification homology, this four category with its 0, 1, 2, 3, and 4 levels. So over here, it's tangles at the 3 level, and KH, T1 union T2, as the home space between a tangle T1 and a tangle T2. But over here, there's another four category. You can think of tangles as forming a four category themselves, but without thinking about Categorification homology at all. So it's the same as we've said over here for 0, 1, and 2, just boring at level 0, 1, and 2. It's just tangles here. And now, a different thing that we could put here for the home from one tangle to another tangle are the tangle cobordisms. So one way of saying that Categorification homology is functorial is saying that there's a functor from this four category to this four category that does nothing on all these low levels, and given a tangle cobordism, that's just the tangle cobordism now is just some surface bounding this link, and it shows you the corresponding line of Categorification homology. So this is sort of like thinking. I promised I'd do something one level lower.
Do you need to change the three morphisms to the right side?
No, I'm going to leave those the same. So the point here, when you think about this functor here, it's important to realize that this functor is certainly not surjective. There are elements of this home space here, that is elements of the Categorification homology of this link that we made by gluing together the tangles, which are not realized by any surface bounding that link. Nevertheless, even though there's stuff here that's outside of the image of this functor, there's still a well-defined operation composing these morphisms using that map that we had on the file over there.
Maybe it's the identification, where you actually are applying the sort of category initialization to get an actual format of
Okay.
identification of different cohomologies.
So let's maybe let's just do that explicitly, and to hell with the rest of my talk if we need to explain this. Here I described sort of, I admit I did this a little bit confusingly, in that I tried to show you this four category in sort of as a sort of conventional four category, showing you 0 and 1 and 2 and 3 and 4 morphisms. Whereas with the definition that I really want to work with, all that I have to specify is for each ball with appropriate boundary conditions, a vector space. So what's this? Well, we take a ball with a link in the boundary. So this is a 4 ball with a link in the boundary 3 sphere. The cohomology 4 category is associating to this the vector space KH of L. Okay? Now I also need to show you if I have some ball that's split up into smaller balls, okay, and I have, I guess I'm going to have to, let me go up a dimension so it's a little bit easier to see. But this is still a dimension lower than it needs to be. And say I have some link on the outer boundary, so that crosses from the northern to the lower hemisphere. And another, but I can also think about the boundary of just the upper solid hemisphere. So I should have. Can people understand this picture? Maybe I should have a different color. So here, if you just look at the boundary of the upper hemisphere, there's a link. Okay. In the boundary of the lower hemisphere, there's another link. This piece and this piece. And in the boundary of the whole thing, there's another link where I ignore this piece and just follow the figure eight. Okay? So here we have every single ball in the picture has a link on its boundary, and they're all compatible where the boundaries agree. Okay? So now, if I give you an element of the cohomology of this link, so I give you X in the cohomology of that guy, and Y in the cohomology of the boundary of the lower surface, which looks like, I really should do this in 3 different colors, it would make life much easier. Okay? From those elements X and Y, I need to tell you something in the cohomology of the outer link. Okay? And there's an obvious cobordism. I can take these knots, take a disjoint union of the 2 knots, and then sort of use some saddle cobordisms to cancel out the shared piece of boundary. And so the functoriality of cohomology tells me how to produce this map. So for any way of chopping up a big ball into lots of little balls, links decorating all the boundaries, elements of the cohomologies of all those internal balls, then I get an element of the cohomology for the link on the outer ball. Okay, so that's the 4 category in this set. So now, what's the 4 manifold invariant described like this? I shouldn't erase that. Okay, so now.
What if they don't match up and it's 0?
Well, no, I don't have to specify the map there. I mean, the map is only defined. The gluing map is just defined on the subset of the tensor product where all the boundaries agree. I don't like saying things are just 0. You should say they're not defined. But I know I'm in the minority. Okay, so here's some 4 manifold. W4. Okay? And I have some specified link in the boundary. What is this vector space that we're going to associate to this link in the boundary of a 4 manifold? Well, what you should do, a generic element of this vector space we associate, you should chop up this 4 manifold into a whole lot of balls, pick boundary data, so that is draw links that are on all of the boundaries in any way you please. but subject to the condition that on the boundary, the links you draw are just this red one that we're planning on working with. And then you take the tensor product of the Covano homologies of all the links you see. Now, that description so far is just the fields on W4. It's not the TQFT vector space. Now we quotient by the relationship. Anytime you glue two balls together, you identify the element before gluing with the element after. Okay? Is that? Okay. Now, so that's sort of, well, the good news. I get to tell you, hey, there's an invariant or four manifold with a link in the boundary. But it's a useless, stupid invariant. It's probably infinite dimensional. It's totally impossible to compute. I mean, this description I gave you while the definition is some co-limit over some gigantic, awful thing. You're never going to do anything. You either need to use something like the gluing formula I had before, or maybe you could hope that the same approach that we use to compute the Covano homology of a usual link might hold. And that approach is the fact that there's an exact triangle telling you what happens when you resolve a crossing. So that's drawn over on the left-hand side. So say I tried to apply that to some link in the boundary of a four manifold here. Say I looked at this crossing here and thought about the two different resolutions. Okay? Certainly there are three different vector spaces that are associated with these three different links. But the exact triangle fails. And you shouldn't be surprised that it fails, essentially because these vector spaces you're associating are some giant quotient of the Covano homologies of lots of little balls. And when you take quotients, exactness isn't preserved. And we have actually done one calculation of this. So if you look at B3 cross S1, which is a pretty boring four manifold, and you look at three different links, it's one crossing knot in the boundary of B3 cross S1, and it's two resolutions. I won't claim that we have definitively really worked out the answer for what this invariant associates to those three different links, but we think we have, and the exact triangle doesn't fail. You don't expect it to work, and it appears to not work in the one example we can try and cover.
Yeah, if it works for normal topic, not switch or normal topic.
I don't know, but I think that's a good question. Well, the one thing we do know actually is that this crazy definition. If you do this crazy definition for a knot in the boundary of the four ball, then it really does give you the right answer. It just gives you the usual Covano homology, not some quotient. So in that case, the definition is not a disaster. Okay. So anyway, the exact triangle fails. Boo-hoo. Computations are maybe hopeless. Okay. What's the whole point of the blob complex? The whole point of the blob complex is to do something better than this TQFT construction, where some shadow of that exact triangle survives. And this is true. If I still have any time left after this slide, I'm about to tell you what the blob complex is. And what we can see is that there, instead of having a long exact sequence relating the Covano homologies of the three different resolutions, so let's put those here. And continuing on for the other homological heights. Instead of having this long exact sequence, these Covano homologies appear as the zeroth graded piece of some blob complex, but there's higher stuff. There's B1, or the first homology of the blob complex for this guy, and the first homology of the blob complex for this guy, first homology of the blob complex of this guy, and so on up, all the higher pieces. And there's a spectral sequence here that collapses to zero. Now, that means that if you, it means that there's some hope of computing just this entry here, the Covano homology, the thing you want, by first computing some of these higher pieces, the higher blob complex pieces of the resolutions, and then using the spectral sequence. But that's far from actually being done here. but that spectral sequence is there. It potentially gives you a way of computing this invariant. Okay. No more motivation. Let's say what on earth this thing is. The blob complex. Okay. So, does anyone know what time I started? Jake, do you know? Oh boy. Okay, sure. I will definitely not get through this job. So, what is it? What we want to do is, so we need to associate a complex to an arbitrary n-manifold. But what we want to make sure of is that if that n-manifold is just the n-ball, then what we're doing is producing a resolution of this quotient, A of n. Okay? And pretty much that determines the definition. So let's just start. I'll show you the low levels first of the blob complex and then the general level later on. So the zeroth chain group of the blob complex are just all fields on the manifold M. Okay. What about the first group, the first vector space? Okay, so it's this vector space generated by triples B, U, and R. B here is some embedded ball, a blob, inside our manifold. U is a field just on B, such that when you evaluate it, you get 0. Okay, so remember, this U is a choice of ciliation of the ball B, along with an element of the appropriate vector space for each cell in there. But when we evaluate it to get an element of the vector space for the whole ball, we have to get 0. Okay, and R is a field on everything else. Okay, what's the differential from B1 back to B0? Well, forget about the ball. We just need to produce a field back there. Take the field U and glue it together with the field R to produce a field back on the entire manifold. Now, it's immediate, just from the definitions, that the zeroth homology is what I define to be the TQFT space. It's just all fields modulo those which evaluate to 0 inside some ball. Okay? So if I just stopped there, I have this little complex B0 and B1, its zeroth homology would be what I want, but there'd be higher homology. The rest of the definition is just in the case where the manifold is just a ball, the rest of the definition is just designed to kill off any higher homology we might have. And for other manifolds, well, there is higher homology. Okay, so here's B2. Now, B2 splits up into two pieces, B2 disjoint and B2 nested. The vector space B2 disjoint is generated by these 5 tuples. You have a pair of disjoint balls. Inside each of those balls, you have some field on the ball which evaluates to 0. And outside the balls, you just have any field you like. And then the differential is just, well, either you move the first ball and glue its label together with the outside ball, glue its label together with the outside label, or we move the second ball and glue its label together with the outside label. B2 nested consists of a pair of balls. This is probably very faint. That's meant to show one ball nested inside another ball. The label on the innermost region inside B1 has to be a null field, something that evaluates to 0. But then we also have a field in the annular region, and that can just be any field you like, and then a field in the outside region. And again, the differential is some over ways of erasing a ball and gluing the appropriate things together. You could just say, check that this term here really is an element of the vector space on the previous slide, B1. We need to check that when you take U and glue it together with R prime, we still get something that evaluates to 0. But U itself evaluates to 0, so sticking more stuff on the outside ensures that it still evaluates to 0. Okay? And then the general definition, you can probably guess from this point. BK consists of K blobs. They're all properly nested or disjoint. You have to label all of the regions that the balls cut the manifold into by fields. Any field that you want to put on an innermost blob, the most deeply nested ones, have to be null fields, ones that evaluate to 0, and the differential is just the sum over ways of erasing blobs. Okay, so the definition, after all of that 40-minute preamble, wasn't actually that bad. And we checked immediately in the definition that it really is, that H0 really is the TQFT scheme space. So in the remaining time, I just want to very quickly say again or say again some things and say a few new things that we can prove about the blob complex. So first of all, something that I said right at the beginning, I'll do this very quickly, is that when n equals 1, this recovers the Hochschild homology of your category. When you try and do the TQFT, the usual TQFT construction on an associative algebra or a one category, you get the coinvariance of that algebra. So the fields on the circle now are just label some. Actually, this picture is kind of a dual picture. I apply Poincare duality to this picture. Really, what I should do is take the circle and chop it up in intervals, label each interval by an element of the algebra, but then we have the relation that you can combine any two intervals you like and replace the label with the product of the two labels. And so it's easy to see that vector space is just the whole algebra A modulo the relation that AB equals BA. Okay? So that's coinvariance. And the blob complex, we get Hochschild homology instead, which is Hochschild homology is the derived version of the coinvariance function. H0 is coinvariance, and the higher H's, the higher homologies, the blob complex, are the higher Hochschild homologies. But you get some pretty nice structure on the blob complex. So here, there's this crazy chain map. Look at singular chains on homeomorphisms of your manifold. Tensor product of the blob complex, the map to the blob complex. This is just saying you can take a k-parameter family of homeomorphisms of your manifold and act via a sort of degree k raising operation on the blob complex. If you just look at H0, this is just the mapping class group acting on the skein module, but you get more stuff. I mean, if you pick a rational slope on a torus, then by looking at the one parameter family of rotations along that, you get a degree 1 raising operator on whatever the homology is. So this property actually sort of constitutes the bulk of our paper proving this. It ends up being very technical in several different directions, but once you have this, it sort of lets you do everything else that you want to learn about the blob complex afterwards. So let me just give you a very brief idea of how you construct this map. This is very schematic. So first of all, if your manifold M had just been a single ball or a union of balls, then there's sort of not much to do. By design, the blob complex was contractible. It contracted back down to the original vector space C of B. And so there, up to homotopy, there's not much choice that you can make for this map. Similarly, if M is a union of balls, the same thing applies. So now what we want to do, say I have some arbitrary k-parameter family of homeomorphisms, moving my manifold around. And the nasty piece of differential geometry is that you can write that k-parameter family of homeomorphisms. You can chop it up into lots of small pieces. You can homotop it first and then chop it up into lots of small pieces. So that on each small piece, we're not moving the whole manifold around, we're just moving things inside k different balls, where we can make those balls as small as we like. We can choose an open cover and do this. And so once we've realized this, that up to homotopy, a k-parameter family of diffeomorphisms is actually supported in some small balls, this shows us that if this chain map exists, it's unique. It's determined by the essentially unique map we noticed in step 1. And then the long and complicated bit in step 3 is saying, well, there are a ton of choices we could have made along the way in choosing how to homotop things to be local and so on. And you have to go through and check that you can make all those choices consistently. But you do get this map. Okay, so just like a TQFT invariant had a gluing formula, there's a gluing formula for the blob complex of a manifold. And I think actually Peter and Robert and Dylan's talks have actually kind of, in some sense, given you a good warm-up for this, because the gluing formula is all in terms of tensor products of array infinity modules. I would love there to be some explanation of these tensor products of array infinity modules having anything whatsoever to do with theirs, but it's no more than something that I would like. Okay, so what we want to say first is that if you have n minus 1 manifold y, and you cross it with an interval, the blob complex of that gadget is naturally an A-infinity category. If you have y inside the boundary of x, then the blob complex of all of x is naturally an A-infinity module over the A-infinity category for y plus I. And then the gluing formula is essentially exactly the same as what we had before for TQFT, but now we have to take the A-infinity tensor product of our bimodules, not the usual tensor product. Now, the A-infinity, if you have a bimodule and you take an A-infinity bimodule and you take the A-infinity tensor product, this is just the Hochschild homology of the bimodule. And so this gluing formula is actually telling you that given a particular handle decomposition of the manifold, you can think about all the handles disjointly at first, compute some bimodule structure on them from the gluing maps, take Hochschild homology, compute some new A-infinity structure on those, depending on the gluing of the two handles to the one handles, compute Hochschild homology of that, and do an iterated Hochschild homology calculation. In practice, that's extremely intimidating and hasn't actually been done. Yep.
And I sort of don't understand this for things like one handles. What do you mean?
So all that I'm saying is, say I just wanted to do something dumb and just cancel off a one handle by gluing a two handle on. So I think of my manifold is the 0 and 1 handle as one connected component, and the two handles as another connected component, and y is the annular region that we're about to glue along. Okay, so there's now this action because we have two copies of this annulus in the boundary. There are these two different actions of the annulus cross I, and all we're doing is identifying those two actions, and that achieves gluing that. So it doesn't really matter the shape of the manifold you're gluing on. It's just some codimension one manifold line. Okay, and then at the very end, let me show you two kind of fancy applications of having the blob complex. So we can. This is very closely related to that action of families of diffeomorphisms. We get something that you might call the higher Deligne conjecture. So the Deligne conjecture, one of many Deligne conjectures, but the relevant one here, says that if you take Hochschild cohomology of an algebra, then you get an action of the little disks operand on the Hochschild cohomology. And we have an analog of that on the blob complex world, but that applies to higher dimensional things as well. So, say I have some manifold M with some boundary of M, that blobs on M form an A-infinity module over blobs on the boundary of M, and so I can look at home from blobs on M to blobs on M that respect that A-infinity action. Okay? And I'm going to call that blob cochains on M, just for the sake of a name. If you specialize to the case of M being an interval, then this thing is exactly the Hochschild cohomology complex. Okay. So the theorem is that you get an action of the n-dimensional fat graph operand on blob cochains. So a typical element of this operand is a picture like this. We start with some manifold M0, and then we pick some submanifold M1 and cut it out and replace it with another manifold N1. And then after that, we chop out some other manifold M2, replace it with some manifold N2, finally we chop out M3, replace it with some manifold N3. That's kind of a piece, an element in the lowest grading of the fat graph operand. But now we allow k-parameter families of these things. So just before we cut out M1, we could consider some k-parameter family of diffeomorphisms of M0. Or at any of these intermediate points, we could take some mapping cylinder or higher order mapping cylinder instead of just doing the surgeries one after the other. And we can also do things like change the order of surgeries if they're far apart. Okay, and a proof not much more difficult than the fact that homeomorphisms act on the blob complex show that you get an action of this n-dimensional fat graph operand, and in the n equals 1 case, that's the Deligne conjecture.
That known before?
Yeah, I mean there have been half a dozen proofs of the Deligne conjecture by now. I could maybe claim that this proof is sort of the friendliest to people who don't know any homotopy theory, but that's a reflection of the fact that Kevin and I don't know any homotopy theory, and so we've kind of gone a roundabout route to do. Okay, and then finally, there's another nice thing that you can do with the blob complex. So say I fix a target space T. I can construct a certain n category consisting of maps from balls to T. So unfortunately, I sort of skipped over something here. N categories are meant to associate a vector space to every ball, but there's an A infinity version of this that associates a chain complex to every ball, and this is the one I'm talking about here. So this n category, which is sort of like the fundamental n groupoid of T, associates to some ball B singular chains on the space of maps from B to T. Okay, so it captures everything about mapping balls into your target space. Now this is an n category, so we can use it as the coefficients in a blob complex calculation. And the theorem is just that when you take blobs on M with coefficients in this fundamental n groupoid, you recover all maps from M to T. And I think the reason to show off this theorem is that it's approximately a generalization of something that Lurie does in his derived algebraic geometry part 6 paper. So in the case that the target space is n-1 connected, so maps of k spheres up to k equals n-1 are all contractible, then in that case, this n category that we've defined here is actually just an En algebra, an algebra for the operand of little n balls. And in that case, for an En algebra, he defines something called the topological chiral homology, given an En algebra and n manifold. And we certainly haven't done this, but we presume that the correct translation is that in the special case of n categories that are trivial at all the bottom levels, that is, those things are En algebras, then his topological chiral homology agrees with the blob complex. But the nice thing is that this theorem doesn't require the assumption that T is n-1 connected, because we don't insist that our n categories are trivial at all lower levels. Yeah, I'll leave it there. That's it.
Questions? Do you have a strategy to prove the non-conjecture is easy on Invariant?
Well, so this definition I talked about for the Corona homology of a link in the boundary of a four manifold, it has a corresponding Lie homology version, and it's plausible that you can prove the same sorts of inequalities that give you genus bounds. But we haven't looked into it beyond seeing that there is a Lie homology version. We haven't tried to prove any genus bounds, something like that.
I was confused, but so you get an invariant for a closed form manifold? Maybe take a ball out of this?
Yeah, so I mean, these manifolds don't have to have boundary. Yeah.
Would it be like so they're sort of in the homology of these sense?
No. I don't think you should expect that it's finite dimensional for.
Okay, so is this kind of perpendicular or different from this thing that I get map determinants before you drop the category level?
Oh, I see. Yeah, no. I mean, yeah, this is associating doubly graded vector spaces to things. Okay, so one important thing to say about that is that when you run the TQFT story as I described it today on a, say, a modular tensor category. So a modular tensor category you actually meant to think of as a three-manifold. As a three category. So according to the recipe I gave today, it should be associating vector spaces to three manifolds. And if we're lucky and some extra conditions apply, which they do for modular tensor categories, numbers to four manifolds, which isn't what we're used to thinking about for arithmetic and derived stuff. Actually, what happens is that these invariants, defined this way, depend only very, very weakly on the interiors of these manifolds. So what we're doing there is, when we want a numerical invariant for a three manifold, we pick a four manifold that it bounds, and then do some normalization factor to do with the signature of the four manifold we chose, and take a number we got for there. Correspondingly over here, it's entirely possible that this invariant depends weakly or not at all, who knows, on the interior of the four manifold, in which case it would be boring for all closed four manifolds. We have no idea.
Other questions?
Yeah.
Why do you call it blob complex? Can you cut out this blob?
Yeah. I mean, it's. I guess I didn't do this on any of the pictures today, but like when you draw these embedded balls for the blob complex, we call them blobs, not